Welcome to the 6th episode of Involution series. In this video, we will look into the dual of Desargues involution theorem which we learnt in the previous episode. So first, we have to understand pole-polar conversion preserves the cross ratio. And then we are going to do the pole-polar conversion for the Desargues involution theorem, and that takes us to the dual space in which we will see a different variation of Desargues involution theorem, and we label it or name it as the dual of Desargues involution theorem. This can be often observed in intricate configurations in geometry. So first, let's learn about the prerequisites. Let's remind ourselves of pole-polar conversion which we learned in the previous episode. Suppose if you have a point on the 2D plane and you are interested in finding the polar of that point. Pole usually refers to a point, polar refers to a line associated with that point. At first, we invert the point P about the circle to get the point P star. Then a perpendicular to OP through P star is constructed, which yields we get the polar associated with the point P. And in order to convert a polar to the corresponding pole, we drop a perpendicular and invert that point. Alright, now the preservation of cross ratio when you have pole-polar conversion. For this, we are going to consider a circle and 4 collinear points lying on a line, and we are now going to find the polars associated with each of these points. We will be getting 4 concurrent lines, and turns out that cross ratio of these 4 lines would equal the cross ratio of the underlying 4 poles of them. As you could see, here's the diagram. You can see that there are 4 points, namely A, B, C, D on the line L. What we did? We just found the polar of A, that is this line. This is called pole, and the polar of that point will be the line highlighted, and polar of B will be this line in blue, and polar of C will be this line in green marked as LC, and polar of D will be this line LD. Let us also mark LA and LB. First, why are they passing through a common point? Why are they concurrent? Well, by the Lahay's theorem which we discussed in previous episodes, we get that the polar of ABCD passes through the pole associated with the line L. All 4 points lie on the line L. When you consider the pole of line L, all these polars shall pass through this point. Therefore, you have a common concurrency. We now observe that the cross ratio of these 4 lines equal the cross ratio of these 4 points. Why so? First of all, let's understand the definition of polar. LA is the line constructed perpendicular to OA passing through the point of inversion A star of A. Similarly, you extend OB and it will be perpendicular to LB. You extend OC, it will be perpendicular to LC. OD will be perpendicular to LD. The feet of perpendiculars are A star, B star, C star and D star, respective point of inversions. Let's label the inversions as A star, B star, C star and D star. As you could see, O A star K, O B star K, O C star K and O D star K equal 90. Therefore, they all lie on a common circle with OK as the diameter as described. And now, consider the circle with all these points as gamma. Then, the point O as the point of perspective, I project the points A, B, C, D on the line L to the circle gamma, and then those projections will form A star, B star, C star and D star. Now I project these 4 points with the point of perspective at K, and that will create the lines LA, LB, LC, LD. You could see that KA star is LA, KB star LB, KC star LC, KD star LD. You get 4 lines with the same cross ratio as those 4 points. Therefore, the pole-polar conversion preserved the cross ratio. This is going to help us tremendously to move from the actual space involving the Desargues involution theorem to the dual space that implies the dual of Desargues involution theorem. Effectively, they are the same, just you are viewing it with the spectacles that does this pole-polar conversion. And since it preserves the cross ratios, it has the involution map preserved. Let's take a closer look. So as we discussed in the previous episode, you have the Desargues involution configuration. So we discussed that W1, W2, X1, X2, Y1, Y2, Z1, Z2 form involution pairs. Involution pairs on that line of concurrency. Call the line of concurrency as L, on L. And now we are going to convert these involution pairs into concurrent lines. We know that involution is also defined in concurrent lines. So let's see how it turns out. First, we construct the polar of A. So it would be the line tangential to the circle at A, because A inverts to itself as it lies on the circle. We get a tangent like this. Then tangent at B will be the polar of B. Tangent at C, the polar of C. Tangent at D would be the polar associated with point D. So thus, we converted the points A, B, C, D into lines. Okay, how come we now think of a random line L in the space? Well, a line is a polar and effectively turns to a pole after this conversion, which is a point. So the line goes off to some point, and since the line is random, it is equivalent to assume that a point P is considered at random in the space. This is just the line L after the pole-polar conversion. Alright, how is x1 defined? How to view x1? Well, x1 is a point and here it will be a line. Notice that by Lahaye's theorem, since x1 belongs to the line L, the polar of x1 shall pass through the point P, which is the pole of line L. So we got one point on the polar of x1. We still need to get one more point to define that line. x1 also lies on AB, the line AB. Well, notice that the pole of AB is simply the intersection of the two tangents, because I know that pole of AB should pass through both the polar at A, the polar of A, and the polar of B by Lahaye's theorem. Therefore, it is the intersection. This is in fact a beautiful property to be noted. Let's call this point as W. Then W will be the pole associated with AB. So therefore, x1 lies on AB shall imply that W lies on the polar of x1. And we conclude that PW is the polar of x1, the line PW. Next, CD. We have to think of x2, and x2 lies on CD as well as line L, which means polar of x2 passes through P as well as the intersection of tangents at C and D. Let's call that to be Y. Then PY denotes the polar of x2. And you can extrapolate this argument nicely to have the intersection of tangents at B and C as the pole of BC. So PX will be the polar of y2 and pz will be the polar of y1. What about z1? Well, for that, we consider the intersection of tangents at A and C and the intersection of tangents at B and D for pole of AC and BD respectively. Then we construct the lines with P, and that creates the two polars associated with Z1 and Z2. For W1 and W2, the polar of W1 is just tangential to the circle and it also passes through P. Therefore, constructing the tangents, two tangents from P to the circle shall give you the polar of W1 and W2 in some order. So they form four pairs of lines that are concurrent at point P, thereby four involution pairs. So let's have the exact diagram in a bit convenient way. So as you could see, here we have completed the quadrilateral ABCD, and equivalently I am regarding the points W, X, Y, Z of the previous quadrilateral as A, B, C, D, and the opposite sides intersect at E and F. So if you connect it with point P, PA and PC shall form one involution pair, one of these four involution pairs. That was associated with X1, X2 being involution pair in the actual space. This is the dual space. So you have PA and PC. Now, join PB and PD to form another involution pair, PE and PF to form the third involution pair, and the fourth one is formed by dropping the tangents from P to the circles. That is associated with W1 and W2. Now, the reason why they are actually preserving this involution pair is that cross ratio of these structures are preserved. X1, X2, W1, W2, Y1, Y2, Z1, Z2. When considered the cross ratio with these converted structures, it is going to be the same. Therefore, if they were involution pairs before, now in the dual space they are again going to be the involution pairs as they preserve the cross ratio, because that's the main property of involution, right? So now we have PA-PC, PB-PD and PE-PF, and the two tangents let's call T1 and T2, PT1, PT2 are involution pairs. Observe that previously we had cyclic quadrilateral and now we have a tangential quadrilateral in which you can inscribe a circle touching all four sides of the quadrilateral. This is true for any general complete quadrilateral, and this is the statement of Desargues involution theorem. Let's take a look at the actual diagram. So this is how the actual diagram looks like, with a neat portrayal of the lines joining from P to the intersection points. So this is used when you have some two pairs or like a random point P that cannot be handled nicely, or when you have two involution pairs and you want to invoke other involution pairs and use it for solving. We will also solve one problem in the upcoming episode, and stay tuned then. Bye.